Good morning, everyone. Today, my discussion is all about the chapter 15, Shifting Gears Alternative Energy. Modern life demands huge amounts of energy, which has historically come from fossil fuels, the coal, oil, and natural gas. These fuels are limited in supply and are major contributors to global warming and pollution. We are at a critical point where we must find ways to harvest energy more efficiently and turn to renewable energy sources. Resources that are continually replenished by natural processes like the sun, wind, and water. So, at the end of this lesson, the students shall be able to discuss the different alternative energy sources and the efficiency capacity of the energy sources. Determine the importance of energy conservation through a group activity, and recognize the significance of alternative energy sources in our daily living. So, now let's start our discussion. Let's first tackle the biomass and biofuels. The biomass, or also called the organic fuel, biomass is a plant or material or animal waste that is burned as fuel. It's the most common fuel in many parts of the world. Examples are the wood, dung, and animal refuse. It is considered renewable if the biomass, like trees, shrubs, crops, is quickly replanted to replace what is harvested. The CO2 releases when biomass is burned is theoretically balanced by the CO2 absorbed by new plants as they grow through what we call the photosynthesis. This process aims to maintain a carbon balance and is a significant advantage over fossil fuels. So while burning biomass, it releases carbon dioxide or the CO2 the plants grown to place. It absorbs an equivalent amount of CO2 through photosynthesis. This creates a theoretical carbon balance over time, distinguishing it from fossil fuels. Now, the biofuels, or the liquid fuels that can partially replace fossil fuels for transportation and heating. These are made from vegetable oils or the soybeans or algae. Algae is particularly promising because it can be farmed in systems that require less land and fewer inputs, like fertilizer, than traditional crops. The ethanol, it is a liquid biofuel made from crops like corn, sugarcane, or switchgrass. A case study highlights Brazil's sustainable fuel economy, which is based on sugarcane ethanol and requires less energy input than corn based ethanol. So, the purpose of biofuels, or what we call the liquid or gaseous fuels, used to replace gasoline and diesel primarily for transportation. Now, the ethanol that are made from starches and sugars in crops like corn, sugarcane, or switchgrass. Brazil is a leading example, basing its fuel economy on sugarcane ethanol, which is a more energy efficient crop for this purpose than corn. The biodiesel that are made from vegetable oils, such as those from soybeans, that algae represents a high potential source as it can be grown without occupying arable land and provides high energy returns. So now let's tackle the methane gas. The methane or the CH4 is produced when organic matter decomposes in low oxygen environments like landfills, wetlands, or animal guts. The benefit of methane gas is capturing and burning this gas provides energy, and the resulting biomass can be used as fertilizer. The environmental imperative of methane gas is this is a potent greenhouse gas, trapping about 25 times more heat than CO2. So, therefore, using it as a fuel rather than letting it escape to the atmosphere is a crucial climate benefit. Now, let's go to harnessing energy from water, or the damming rivers, or what we call the hydropower. The mechanisms of hydropower is it captures the kinetic energy of flowing water. A dam creates a large reservoir. The water flows through a pipe or a penstock to spin a turbine, which is connected to a generator that produces electricity. So, for reference, this can be seen in figure 15 in the handout that shows this simple hydropower system. So there are problem with large dams. So there is a case study from Three Gorges Dam. While providing huge amounts of clean energy, large dams have massive negative consequences, including destroying habitat and damaging river ecosystems. Also, flooding extensive watersheds and displacing communities. So there is a solution for this. They call it the small scale systems. Scientists are developing new technologies such as small floating kinetic energy systems that capture the natural flow of the river without building a large dam or causing widespread flooding. So note, hydropower plants boast high energy efficiency, often reaching 90% due to minimal energy loss in the water to electricity conversion. So modern solutions for this is new technologies such as small floating kinetic energy systems are being developed to capture energy from river currents without the need for large environmentally disruptive dam structures. Now, let's dive into the tidal and wave energy. So, what are the mechanisms for this? These systems take advantage of the predictable, twice daily rise and fall of the ocean tides. So, in a tidal energy system, the kinetic energy of the tidal flow is captured, spinning a turbine that converts the movement into electricity. So, example of this is from the case study of the Siwa Lake Tidal Power Station in South Korea. It uses a barrage to capture tidal flow, generating electricity and helping maintain water levels for conservation. So there is an advantage and disadvantage for this. The advantage is tides and waves are a constant, unchanging, and clean source of energy, while the disadvantage, they can impact the environment by changing the flow of water into shorelines and estuarine ecosystems. Now, let's tackle the part of the geothermal energy. Now let's have first the geothermal power plants. So the geothermal energy uses the heat produced by the radioactive decay within the Earth's interior. So the mechanisms for geothermal energy is in some regions, naturally occurring steam or hot water is brought to the surface to drive a turbine and generate electricity. So this resource is geographically limited to certain regions. So this energy comes from the Earth's internal heat, primarily from the slow decay of radioactive elements deep within the crust. So in certain geological areas, naturally occurring steam or hot water is tapped from underground reservoirs and used to drive turbines for electricity generation. So this is a highly reliable source resulting in a very high capacity factor. Now, let's have the geothermal heat pumps. So there is a widespread use for this. So this is a simpler, highly efficient system that is widely available. It relies on the principle that the Earth's temperature just below the surface is warmer than the air in winter and cooler than the air in summer. So, the function for this is a heat pump circulates fluid through underground pipes to transfer the heat. So, in winter, it brings the Earth's warmth into the house. And in summer, it removes heat from the house and deposits it into the ground. So, this is the common application. It relies on the stable year round temperature of the shallow ground, warmer than air in water and cooler in summer. So, a pump circulates fluid to exchange heat. So, it heats the building in winter by drawing heat from the ground and cools the building in summer by transferring heat back into the ground. So, the conclusion for the energy efficiency metrics. So, the development of these alternative energy sources from biomass to geothermal is very essential. They are clean and renewable, reducing our reliance on limited, polluting fossil fuels. So, when evaluating any energy source, we need to consider three concepts. These are the capacity factor, conversion efficiency, and community and environmental cost. So, for the capacity factor, the ratio of the actual energy produced to the maximum possible energy that could be produced. It accounts for downtime, for the maintenance or the periods when the fuel source isn't available. Example, wind isn't blowing. That's the example for this. While the conversion efficiency describes how much of the energy input ends up being useful energy. For example, a modern coal plant is only about 30% efficient, whereas a hydropower plant can be around 90% efficient. So that's it. While community and environmental cost, this must always be factored into the total cost of energy, especially for large scale projects like dams. So, to conclude everything, to successfully transition to a renewable energy future, we must consider efficiency, capacity factor, cost, and the social and environmental impacts of every alternative sources. So that's all for my discussion. I hope you learned something from this. So thank you so much for listening.